This lesson deals with a CMOS NOR gate. You can find these notes in the ECE302 ebook in Chapter 4 on page 44. In our last video, we took a look at an inverter using CMOS transistors. In this configuration, I've got two transistors with their drain and source in series and two in parallel. We saw that MOSFETs used as logic elements were either high resistances or low resistances. So let's model this transistor M1 as a resistor between these two nodes, and then this one between these two nodes, and then this one here, and then this one here. And I'll just label these as having a source to drain resistance or a drain to source resistance. In our previous analysis technique, we took a guess and then solved for the voltages in the logic gate, and then solved for the gate to drain or the drain to gate voltage, and see whether it was consistent with being in the ohmic region or being in the cutoff region. That technique won't work well as we get more transistors in these internal nodes because we don't really know the exact value of these resistances. We're just guessing that they're big numbers and small numbers. So I need another technique for being able to take a guess and to verify my guess. Let's go back to page 12, where I've got the VI characteristics of a N-channel MOSFET. If the gate to source is greater than threshold, I'm either in the ohmic region or I'm in the current saturation region. But if I'm in the current saturation region, the current up here is something in the milliamp range or the hundreds of microamps range. If I have a very small current in my circuit, which is typical of logic gates, say nanoamps or microamps, I would be somewhere down in this region over here. If the gate source voltage is greater than threshold, then I would take a guess that I'm in the ohmic region if the current in that transistor is small. Let's use that idea to analyze this NOR gate. So back to page 44. Let me blow this up, make it a little bit easier to look at. With a 5-volt power supply, our inputs are either 0 volts or 5 volts. The first case below here is the case of 0 volts and 0 volts. Let's assume that the threshold voltage is 1 volt, just to make the algebra a little bit easier. You notice here that the bulk pin on the P-channel device is connected up to the most positive potential in the circuit, and for the other P-channel device, it's also hooked up to the most positive potential in the circuit. For the N-channel device, it's actually hooked up to the most negative potential in the circuit, and I'll explain that in a few more pages. Let's find the gate source voltages and the source to gate voltages of the outer transistors. Those are the easiest. So that makes this 0 volts. And that means that this is less than threshold, and this is a large resistance. And put a number on it like we did previously of maybe 1 gigaohm. And likewise here, this gate to source voltage is also equal to 0 volts. A 2 would be in cutoff. That would be 1 gigaohm. This transistor up here, I can get the source to gate voltage. The source is 5 volts, the gate is 0, so there's 5 volts across here. We're greater than threshold. It would either be in the ohmic region or the current saturation region. But if I assume that this current is small, and then later verify it, by small I mean things like maybe in nanoamps or picoamps, then my guess for transistor M1 was that this would be a low resistance. I put a number on this to make it a little bit easier to do the algebra. This says 1 ohm, and these are gigaohms. If the current is small, the voltage across here is a small current times a small resistance. So say maybe you had a nanoamp times an ohm, that would be a nanovolt. This node voltage here would be 5 volts minus something in nanovolts. So this is about 5 volts. Really pretty close to 5. But that also means that this is about 5 volts. Now the source to gate voltage would be 5 volts minus 0 or 5 volts. We're greater than threshold, so I'm going to guess that this is going to be an ohmic, and that would make this a very low resistance. Let's just check if we have a small current. The resistance seen by this power supply is 2 ohms in series with these two in parallel, which would be a half a gigaohm divided into 5 volts. That would be something in the nanoamp range. This was verified. Guesses are correct. Now let's solve for the voltage here. It's going to be 5 volts. So a voltage divider. This is going to be 2 equal resistors in parallel, so this is 1/2 of a gigaohm over 1/2 of a gigaohm plus 2 ohms. I have this number dominating this one, so I roughly have 1/2 gig over 1/2 gig, so this is about 5 volts. Really pretty close to 5, maybe 4.99999. Given two inputs of 0, the output's equal to 5 volts. Let's take a look at the next case, where I've got 0 and 5 volts for V sub A and V sub B. But in order to do that, I need to erase the stuff that's here, so let me do that. We'll start over again. Our next case is having 0 volts here and 5 volts here. Take the outer transistors, those are the easiest one to calculate. This being 0 volts, I'd have 0 volts here. This being 5 volts, I'd have 5 volts here. And this being 0 volts and this being 5, the voltage from here to here would be 5 volts. With a gate to source voltage less than threshold, this would be in cutoff. That would make this, again, a really big resistor. Again, I'll put a gigaohm here, although I don't know the exact value. This is greater than threshold, but I'm going to assume that the current is small. Let me erase this check here because we haven't checked it yet. But if this is small, then we would be in the ohmic region. This would be a low resistance. Again, maybe make that 1 ohm. Here I've got a source to gate voltage of 5 volts greater than threshold. Again, I would assume that this is in the ohmic region and about 1 ohm. Right now, what's the voltage over here? Well, if there's a small current flowing, again, I've got a tiny current times a 1 ohm resistor. If I had nanoamps times this, I'd have nanovolts, and so 5 volts minus something in nanovolts would be, again, about 5 volts. That makes this 5. But now the difference between these two is 5 minus 5, or 0. So that makes this in cutoff, because we're less than threshold, and I would guess that's something big on a gigaohm or so. Is the current coming in small? Well, here I've got 1 ohm in parallel with 1 gigaohm. That's about 1 ohm. That's in series with a gigaohm, in series with 1 ohm. So I've really got 1 ohm, 1 gigaohm, 1 ohm. So I've got 1 gigaohm plus 2 ohms divided into 5 volts. That's again going to be something in nanoamps. So the assumption of small current was verified. Let's solve for the output voltage. The output voltage is equal to 5 volts times 1 in parallel with 1 gigaohm is about 1 ohm over 1 ohm plus 1 gigaohm plus 1 ohm. That's going to be 5 divided by roughly 1 giga, which would be 5 nanovolts, and that's approximately equal to 0. Given a 0.5 input, the output's equal to 0. Again, let me erase the previous results. 5 volts here, 0 volts here is our next case. And our gate source voltage from here would be 5 volts, and our gate to source voltage from here would be 0 volts, and our source to gate voltage here would now be 0 volts. 5 volts minus 5 volts are 0. I'm less than threshold, so cut off, so 1 gigaohm. Here I'm greater than threshold, and if I assume the current is small, then I would be in the ohmic region. Again, this would be maybe around 1 ohm. Here I'm less than threshold. Resistance here would be 1 gigaohm. It would be in cutoff. What's the voltage over here? We've got a small current times a big resistance. It's really multiplying 0 times infinity. You can get any answer you want. But this is a 5 volt power supply and ground, so this voltage is somewhere between 0 volts and 5 volts. I'll call it maybe V sub x. The voltage here is somewhere between 0 and 5 volts. Now, what's the voltage across the source to gate? There's 5 volts here and 0 here. That would be 5 volts, and we would be greater than threshold. Suppose that this voltage here is 3 volts. Then 3 volts minus 0 would be 3 volts, and we'd be greater than threshold. We would again be a low resistance. But suppose that this voltage here was a half a volt. Then half a volt minus 0 would be a half a volt here, and we would be less than threshold. We don't know the value of this resistor. It could be low, it could be high. I'm just going to label the fact that I don't know this value of resistance. How does that affect the calculations? Well, first of all, is the current small? The resistance seen by this battery is 1 gigaohm plus an unknown number plus another 1 ohm. It's at least a gigaohm in size, and so the current is small. We have something in nanoamps. Let's calculate the output voltage and see what this don't know does to us. I have 1 ohm in parallel with 1 gigaohm. Okay, and I'll multiply this by 5. I get roughly 1 ohm divided by 1 ohm plus 1 gigaohm plus a number I don't know. The denominator is a big number no matter what the don't know is. We've got 5 volts divided by at least 1 gigaohm, something on the order of nanovolts, no matter what the don't know is. Approximately equal to 0 volts. It turned out here that the don't know became a don't care. And then for commercial logic gates, that'll be the case. But if you make up your own logic gate, that might not be true. Given 5 and 0, the output is low or 0. Let me again erase this and take a look at the last case. Our last case is having 5 volts and 5 volts. Our gate to source voltage here would be 5. This would also be 5 volts. I got 5 volts here and I got 5 volts here. And then the voltage across here would be 5 minus 5 or 0. These would be low resistances if the current is small. And here I'd have a high resistance because I'm less than threshold. Again, the voltage here is unknown because if the current is small, I've got small times a big, small current times a big resistance. This could be any voltage, but is limited to something between 0, again, I'll call this maybe V sub x, and 5 volts. This voltage here were 5 volts. The difference would be 0. If the voltage here were 4 volts, we would have 4 minus 5 or minus 1. If this was 2 volts, we'd have 2 minus 5. Even though I don't know the value of this, in all cases the voltage here is actually less than threshold. Voltage across here is always a number less than or equal to 0. The value of the resistance here is a large value because we are below threshold for all possible voltages. Is the current small? Well, we've got the resistance seen by this battery is 2 gigaohms plus half an ohm. And we're something in nanoamps. So yes, that does check. Find the output voltage now. It's going to be 5 volts times 1 in parallel with 1 is a half, divided by a half, plus 2 gigaohms, nanovolts, which again is approximately 0 compared to 5 volts. Given 2 5 inputs, I get an output that's equal to 0. Let's take a look at the table below. Here's what we did with our calculations. I did it here with highs and lows, but again, putting numbers in does make it a lot easier to see where the numbers are going. Given 0, 0 input, I had a 5 output. 0, 5, 5, 0, 5, 5, I had a 0 output. This is the OR function negated, what we call the NOR. This is a CMOS NOR gate.